All right, morning, y'all. Just a reminder, so problem set 2 is due today. Problem set 3 is posted now on the stuff we've been doing this week. And I know I haven't gotten problem set 1 back yet, but I will do that soon. I will remember to have a quiz today, so I'm saying it out loud now, so hopefully I'll remember, because I'm notorious for just like getting to the end of class and being like, oh, right, we're supposed to be good. So you can help me remember too. We'll just leave it, 5 or 10 minutes at the end. It'll be it's on rewriting systems. And just as a reminder, the way the quizzes work, it's just graded like pass-fail basically. And if you do not get credit, then you can come to office hours to take a different version or whatever. All right, so let's there we go. Yeah, we'll just use this thing. All right, so Tuesday we started talking about algebraic data types, right? And we saw this was like an enumeration type, and you could do something like this where each data constructor can have package up some data, and the fact that we can have multiple constructors gives us, it's like an OR, gives us options of how to make a value of that type, and then the fact that each constructor can have multiple pieces of data in it gives us the power of AND to combine things together. Okay, and then we also saw a recursive one, right? So what I want to talk about today, and we actually saw this very briefly. I mentioned this data type maybe that took this parameter, which was like a type parameter, and that's what I want to talk about today. So this idea of type parameters, things kind of being generic in the type, is called polymorphism. And one way I want to motivate this is if we think about this type that we made, int list, that's all fine and good if we really just want lists of ints. But what if we want a list of booleans, or if we want a list of trees, or we want a list of lists of, right? It's like, from what I've told you so far, you're like, well, I guess we just have to make a new one for every different kind of list we want. But that seems really stupid, right? Especially because a lot of the code we might write, summing an int list, that really only makes sense on a list of ints, not a list of booleans, for example. But indexing into a list, that should make sense for any kind of list, and it's going to work in exactly the same way. The indexing function doesn't care what kinds of data you're storing in your list, right? So ideally, we'd like a way to just write that code once and have it work for any kind of list, right? And so, indeed, we can do that. So we want lists with different kinds of data. I will use the word types because I literally do mean different types. Different types of data, but be able to write generic code that will work for any type of list. Okay, so let me show you how to do that. So I'm just going to make a type called list, and of course there are lists to find in the standard library, but we're going to make our own for now, and then I'll show you the real ones later. So right before we said something like data list where, and so now, as we already saw with maybe, I'm going to write data list A. And so this A is a type parameter. And let's turn this off. Stand for any type. How does Haskell know that A is a type parameter and list is the name of a type? Well, because it starts with a lowercase letter, right? And this is how, this is one of the reasons why Haskell has that requirement, because otherwise it would be really hard to figure out if you're writing down some type, like which things are types and which are variables. type parameter, or also a type variable. And we can make some constructors just like before. So we'll say, well, I guess I can't use the name empty anymore because I already used that. I don't know, call it. Or, you know what? No. We're going to make a new file. Because now I can use those names again. That has type list A, because an empty list can have elements of any type, right? I mean, there are no elements, so it doesn't matter. And then we can have a cons, and a cons contains a value of type A and a list A, and it constructs a list A. Okay, this is exactly the same as our int list, but just everywhere that we had, we had int here, and I just put A. And so, as an example, I can make a list. We can make a list int, and it will look the same as before. So cons 3, cons 5, empty. Right, that's fine. Or I could make a list bool, which I could have cons true, cons false, empty. Or I could make a list string. Why not? So it'll be a cons, and then something will go there. We'll come back to that. So I want 3 things in my list. And then in each of those holes, I need to fill in a list string, because those are the elements of this list. Yes?
So when you're defining the list, you always have to end it with empty?
The way we've defined list, yes. I mean, well, no. Yes and no. If you want it to be finite, it has to end with empty. But as we saw on Tuesday, you can actually make an infinite list using recursion. We defined a list that was like L equals cons 7L. And that never ends with empty, but because it just keeps going further. But yeah, like since cons is recursive, the only way to stop this is you eventually have to use empty. Cons empty. Cons. This is a little stupid, but I'm really going to get lost in the parentheses. All right, all right, sure, why not? Okay, I mean, so the notation is terrible, and real lists have much better, nicer notation. But the point is, it doesn't matter if you followed all the parentheses and whatever. But the point is, we can literally put any type we want in for A, right? It doesn't just have to be like primitive things like ints or bools or whatever. It could be some even more structured things. Okay, and well, one thing to point out is that if I tried to do, let's say I said list bool, but then I tried to write, cons true, cons 6 empty, right? Of course I get an error. And it says something about numbers and bools, and like it doesn't match, right? And that makes sense because I said I was going to make a list that contained booleans, but I tried to put a number in there, and it's like, no, you can't do that. Right? And so let's think about. So our indexing function from Tuesday was one that I mentioned. What would be some other examples of functions on lists that won't care what type of elements are in the list, that will work the same way no matter what kind of list you have?
Removing the last element.
Removing the last element, sure. Yeah. So we can let's see if we can write that. So remove last. It should have type list A to list A. And so the fact that I put an A here, well, we'll talk more about that in a second. But it's kind of signaling the fact that I want this to be able to work on any kind of list, right? So remove last. How do we write this? If it's, I guess if you try to remove the last item from an empty list, it'll just still be empty. And if you remove the last item from, if you have a cons don't care empty, that is a single element list. And so we can just return empty to remove that one element. And otherwise, you know, it's like cons x, I'll call it, well, okay. Cons A, remove last L. Right, we just sort of say, all right, if you have, starts with A and then there's some rest of the list, remove the last thing from the rest and then just stick A on. By the way, so this is fairly common. So notice, you may not have, I may have gone by too quickly, but so here, A is a variable standing for a type. And down here, I reused the name A as a variable, you know, holding a value of type A, whatever A is, which could either be convenient or confusing depending on your point of view. It's convenient because since we really don't know anything about this type, like, well, there's not like a good name we could give this thing. I mean, you could call it item, I guess. But giving it a name that's the same as its type actually is kind of convenient because it just helps you remember, oh, this is a thing of type A. But maybe you find that confusing, and you could like, you know, give it some different name if you wanted. That's fine too. I'm going to keep it A, but okay. So this is cool, and let's test this out and make sure this works. So if I say remove last, oh, I forgot to put. I'm going to run into. I need to put deriving show. Okay. Let's reload this, and if I say remove last L1, that worked, right? It removed the 5. Or I could say remove last L2, and it removed the false, and this is great, right? It worked on a list of ints, it worked on a list of bools. Okay. We could also do things like we could write a function to compute the length of a list, for example. Right? That doesn't care what the elements are, it just counts them. Or something to reverse a list. Right? There's a lot of examples of these kinds of structural things you can do on a list that don't really care what elements are. Let me show you an example of something that does not work. Let's think about why. If I say like sum list A, and we say, okay, sum list of empty is 0, and sum list of you know, cons x, I'll use x this time, is, you know, x plus sum list L. Okay, that was how we add up everything in the list, but it's yelling at us. If I try to so the error message is talking about, you know, something called num, which we haven't talked about, but it's actually suggesting a possible fix, which would actually work, but that's not where I want to go with this. I mean, fundamentally, the reason this doesn't work is that, right, this type made a promise, and the promise this type makes is, you give me a list of any type you want, right? So the person calling the function gets to choose the type A, and I will return you something of that type, right? But the implementation does not really satisfy that promise because it's trying to do things like, you know, 0 and add things, and how do we even know that the type A chosen by the person calling this function will support addition and 0 and stuff like that, right? We don't. So like, this type promises that it will work even on lists of booleans or lists of strings, right? And you can't like add those things or do 0. So we could, so this type promises that it will work on any type of list the caller chooses. Whoops. But it is a lie. However, we can do something like this. We could say, well, I'll make a more specific promise. If you promise to give me a list of int, I will give you back an int. Why is this? Oh, no, it's not an error. It's, there we go. Okay, I just had to reload it. There we go. My IDE hadn't caught up. So this is fine, right? It's like, okay, now you're saying I will only accept lists of ints, and now you can do things with the ints like add limits. Okay. What questions do you have so far? So I will say, how many of you have used, probably most of you, I'm guessing, but have used like generics in Java? And it's where you have like a class or a thing with like a little bracket, you can put different types in there, right? So interesting little bit of historical programming language trivia. The original versions, like the first versions of Java, did not have that. And they kind of wanted it, but they're like, this is too complicated. We don't know how to do this yet, and so we're just going to leave it out for now. And then it was actually some of the people that had worked on the original design of Haskell, took the way that polymorphism worked in Haskell and went and made a design for Java generics, and actually like implemented a version of it. And everyone really liked it, and they're like, cool. And so then they incorporated that into Java. And so Java generics actually were kind of directly influenced by Haskell's polymorphism. Okay, but let me talk a little bit more specifically about how this works. So this is called parametric polymorphism. And I'll say what that means. So a polymorphic function in Haskell, i.e. a function whose type contains type variables. There's two things that have to be true. So one, it has to work for any type chosen by the caller of the function. Okay, we just saw that before, right? I couldn't say some list would take. This is a promise that some list will take any list that the caller wants. That's why it didn't work for me to use 0 and plus. And the second thing is it has to work uniformly for any type. And another way to say that is the code has to work the same way no matter what type is chosen. Code must work the same way for any chosen type. Put another way, you cannot write a function, for example, what if I tried to write a function that said, I'll take a list A and return an A, and but if A is int, I'm going to add them up. But if A is anything else, I'll just return the first one or something, right? You can't do that. There's actually no way to even express that in Haskell. So your polymorphic functions have to do exactly the same thing, kind of literally have the same code no matter what type is chosen. And this one in particular, I mean, this one, number one, is pretty much the same for a lot of languages that have, like, Java generics the same way, right? Any language that has some kind of polymorphism. Number two is pretty interesting, and that's a little different than other things. So Java, as an example, we were talking about Java. Java definitely does not work this way. Java has an instance of operator, and you can like have an if that asks, is this type an instance of this, and then do different things depending on what type you actually get. There's kind of two reasons for this. And I'll say them briefly now, but you'll see these coming up throughout. So one is it's just sort of it's theoretically kind of nice, and we'll see that it gives us a polymorphic type in Haskell tells you a lot because of this restriction. And the other reason is a sort of practical reason that the way Haskell works is that once your program is type checked, and when it's then compiled to something that will actually run, all the types are completely erased. So when the program is actually running, there's no type information anywhere, right? So when, so this remove last function, for example, right? It works by it literally at runtime, it would pattern match by looks at some bits and decides is it 0 or is it 1, maybe. Maybe those two constructors, empty is represented by 0 and cons is represented by 1. And then, depending on which it is, whatever thing is here, it's all it knows is that there's a blob of bits there, and it just copies them, right? It has no idea what type that's supposed to be, because that information is not there. And that just makes it possible to be a little more efficient, right? So Java, for example, at runtime literally has to, all the values that are going around at runtime, have to have some information about what type they are, because that might be needed. But in Haskell, that can get rid of that. So the types help make sure that your program makes sense, and then once it's checked that it all makes sense, you can just get rid of them, and just work with raw bits and whatever at runtime, because we've already checked that everything's going to work out nicely. We don't need to be checking it while we're running. Cool. So let me show you. I'm going to talk more about both of these things. Let's talk more about number 1 first. This idea that the type is chosen by the caller. So we can actually see. So let me write a simple list length function. So the list length one, it's a list A, and it has an int, right? And if it's empty, we return 0, and if it is a cons, we just say 1 plus the list length of L, right? But I'm going to write this again. Do I need to turn on a, whoops. I forget if I need to turn on, no, I guess I don't. All right. Okay, cool. You used to have to turn on an extension for this to work, but apparently now you do not. So, it turns out that this is really just an abbreviation for this. So fundamentally, anytime you have a type variable in your type, it's as if at the very beginning there's this special thing called for all. One way you can read it is it's just literally saying this is supposed to work for all A. It can be whatever type you want. But it actually literally is secretly, or maybe not secretly, it's a hidden extra parameter to the function. So one way to think of it is this list length 2 actually has 2 parameters. The first parameter is a type, A, and then the second parameter is a list of that type. Now normally, let me write that down. So really, the type of list length 1 is an abbreviation for the type below. Right? When you write this, Haskell looks at this and it's like, oh, you used a variable A. I'm just going to go ahead and stick a for all on the front there for you, since that's what you must have meant, right? And the for all is really an extra parameter. Oops. I thought I turned that off. An extra parameter to the function. But that parameter is normally inferred by Haskell. You don't have to actually write. I'll say a hidden parameter that is normally inferred, right? Because when I called it here, I didn't have to give it 2 arguments, right? I just gave it a list, and then Haskell figured out, it's like, oh, you gave it a list of ints, so you must have wanted A to be int. So I will go ahead and fill that in for you, as if you had said list length to, int L2. It is possible, however, to explicitly pass that type parameter. And we're not going to need this very much, but I think it's just nice to understand how polymorphism is working. We can, to explicitly pass a type argument, you use an at. So I can say like at int L2. Because no, right. L2 is not a list of ints, it's a list of bool. Right. So of course that's an error, right? Because I said, yes, I would like to use the list length 2 function, please, and the first parameter I would like to use is int, and the second parameter is L2, and it's like, no, you said you wanted to use the type int, but then you gave a list of bool. That doesn't make sense. Okay, so that's, but if I said at bool L2, right, it works the same as before. There are situations where you would want to use this if you're doing some more, typically you need it if you're doing some more advanced type things where basically Haskell doesn't have enough information to figure out what type you really wanted, and you might want to fill it in, explicitly. We're probably not going to see any situations like that in this class. But again, I think it's nice to understand that that really is what's going on under the hood. It is an extra parameter. I'll just say we can explicitly pass type arguments using that type syntax. Okay, cool. Questions? Okay. So now let's talk more about this. And so, by the way, this this number 2 that polymorphic functions have to work uniformly for any type that's chosen. This is called parametricity, and so that's the parametric in parametric polymorphism is referring to this this thing. So, and I mentioned that fact actually gives you a lot of information about a polymorphic type. And so we're going to play a little game. I think of it as a game. You may or may not, but so I'm going to write down some types, and then we're going to think about what could a function of that type possibly do. And we're going to see that, if the type is pretty polymorphic, that often strongly restricts what that function can possibly do. And then we'll think about why that's a useful idea. Okay, so let's start with, I don't know what to call these, but we'll just call it, I'll call it P1, P for parametricity. So here's our first example. If I have something of type A arrow A, what could possibly be a function with that type? What do you think?
It can return itself.
What do you mean return itself?
Like, whatever you give it, it just returns it.
Okay, so like if I say P1x equals x, yeah, that works, right? Because it takes an argument of some type A, and then it's supposed to return something of the same type, so you could just return that same thing. Sure. What else could a function of this type do?
Jason?
Could you like concatenate itself so you could take that same A and just add it to itself again and return that A?
Okay, so like, call this P1 prime. So what do you want me to do with, like,
So take that first, essentially double it, is what I'm, I guess, asking. I don't know.
like adding it to itself, or like
Adding to itself, I guess.
like
Yeah.
this?
Yeah.
Okay, that's a good idea, but we're getting a type error. Why? So before I show you what the error is, why do you all think this is an error? Yeah.
It might work for like an integer or a string for concatenation, but I don't know how you can add like a bool or something.
Yeah, exactly, right? So this is kind of assuming that we can do some kind of plus operation on this type, but we don't know that, right? We've promised that this will work on any type you want. You know, whoever calls this function gets to choose the type. It might even be a type that we've never seen before, right? Because someone might make up their own type and then call our function. That's totally fine. So we definitely can't assume that we can do something like adding values of that type. That's a good idea, but yeah, this does not work. It does not work. Can't assume we can add values of type A. Okay, anything else? Okay, so I'm glad that you all are having trouble thinking of it, because there really aren't any other things it could do. Well, okay, big asterisk. There's actually two other things it could do. One is it could crash, and one is it could go into an infinite loop. I mean, you laugh, but that's real. That's a real thing that Haskell functions can do, right? But that's not very interesting. So ground rules, no crashing, partial functions,
That's what I was thinking.
and no infinite loops. Right, because you could define, you know, P1x equals undefined. Or you could say P1x equals P1x. Right? Either of those would be accepted, but one would just crash, one would go into infinite loop. So we do, for this game, like, because the thing is, if you allow crashing or infinite loops, then you can make any type you want. You could write down any old type and you could just make it crash, and it's like, Haskell's like, sure, I guess that has that type, whatever, right? So we're not going to allow ourselves to use those because those are not very interesting. And so other than that, it turns out this is the only possible function of this type. Intuitively, why is that? It's kind of like, well, imagine that your friend handed you a sealed box. And they're like, inside this box is a kind of thing. I'm not going to tell you what kind of thing it is. And also, you're not allowed to open the box. But I would like you to give me back the same kind of thing. You're just like, here you go. Like, there's nothing else you can do because you don't know anything about what's in the box. You cannot open it. You can't, like, there's just nothing you can do. So it's the only possible way you can return something of the same type is just give back the same thing here. Okay. This is the only function of this type. So, you know, in contrast, if you have a function of type int arrow int, that could be like a bajillion different things. It could add 1, it could square it, it could always return 16, who knows, right? But if it's a arrow a, that's the only thing to do. All right, let me give you another one. So P2, a arrow a. All right, chat with each other, see what do you think? What could this do?
Well, you get two inputs. So you can either return the first one or the second one. Is what it is. So P2xy equals x. P2xy equals y. Well, I guess you wouldn't. I mean, I guess you wouldn't actually need the, like, you would say like P1x underscore equals x or P1 underscore y equals y. Yeah, since you
Yeah, so what do y'all think? Could this do? Yeah.
You can return the first parameter, or you can return the second parameter.
Okay, yeah, so I could be like, we'll call this P2A. No, a P2, sure. P2B could, like, do that. Actually, you know what? Just for fun, you can do this. It's occasionally useful. Not that often, but if you've got like multiple things that are all going to be the same type, you can just like put them all in one. Yeah, are there any other functions of this type? Lee?
My guess is no, but would returning a pair of that type be possible, or would that be like different?
Like returning a pair of x and y or
Yeah.
something? Yeah, that's good. That's a good question. But that would not work because that would not have the right type. Like a pair of two a's is not the same thing as an a. Right? That would have to look like, parentheses a comma a or something like that. Yeah, so if, well, that's maybe I could do that as another example later, but yeah, so a pair will not work. What, any other ideas we could do? How about choosing between them randomly? Could we do that? No, we can't. So, but the reason it has nothing to do with parametric polymorphism. It has to do with the fact that, right, Haskell functions have to be functions in the mathematical sense. One thing that means is, given the same inputs, they always have to return the same outputs. Can you imagine in a math class if someone was like, we're going to define this function f of x, and f of x like chooses a random output every time you call it. You're just like, what? Like, that's not a function. That's I don't know what that is, but no, a function, like, it's defined, like for each input it has a specific output that it gives, and so you cannot. So now, what if you want to choose randomly between two things? Yes, we can do that in Haskell, but not with this type. We need to do some more complicated stuff to indicate like that we're using randomness and whatever. But yeah, we cannot choose randomly. It has to always give the same output for the same inputs, and so that means these are the only two things we can do. You can either always return the first thing or always return the second thing. And again, we can't, like, we have no way to combine these two A's because we have no idea what type they are, and so we can't. So, right, these are the only two functions of this type. So I'll say note, can't choose randomly because Haskell functions must be pure, i.e. must always yield the same output for the same input. Or, yeah. All right, let's do another one. Let's see, P3, A, arrow B, B. What do you think about this one?
You think you can just ignore what A is and always return some generic B?
So how, like what do you mean? Like, so ignore A and then return what?
Just B.
B? It says variable not in scope, B. I do not have any variable named B in scope, so.
Can you typecast in Haskell?
Can you typecast?
Like, could you typecast A to B and then just return that?
I mean, well, what is a typecast but a function that takes one thing and returns the other thing? So that's what we're actually asking, essentially, right? Can you typecast? Lee?
No.
Oh, I thought you put your hand up.
Yeah, no. I'm thinking about the show function. How you can like. I don't know.
The
Like,
show
you could-
function. Oh, do you want to use show here somehow? Right. Well, show always gives a string.
I know.
Yeah. Well, it is interesting that you mentioned show, and there's other things that we've seen like plus or less than. You're like, but how does show work? Because it takes anything and turns it into a string, but it has to work differently for different types. So there is a way to have polymorphic functions that work differently depending on what type you give it, that we're going to learn about later. And things like show work that way, also things like plus, less than, right? Because less than doesn't always work the same way no matter what type you give it. Like it does something specific for doubles and something specific for strings and whatever. But yeah, that's something using a different mechanism. Yeah.
So is B just another generic, like any?
Yeah, so think about this, right? This type has two variables in it. And so really it's the same as, for all A, for all B, blah, blah, blah. Which means whoever calls this function, they get to choose A, then they get to choose B, and then they get to pass in something of type A. Right? So this is like this is kind of corresponds to the scenario of your friend says, okay, I'm thinking of two different kinds of things. I'm not going to tell you what they are, but I have them in mind. And I'm going to give you a box that you can't open with the first kind of thing, and I want you to give me the second kind of thing. But I'm not going to tell you what it is. You can't, there's no way you can do it, right? You have nothing. You have an A, but that doesn't help. A and B could be the same. Your friend could decide to choose them the same, but they don't have to, right? Could be int and bool, or list of string and, who knows, right? So yeah, no, this function is deeply impossible. Right? Because it literally is an arbitrary typecast. It's just like, yeah, I can turn anything you want into anything else you want. Like, if this was possible, it just completely breaks the entire type system. Because now you can just call anywhere that you're like, oh, Haskell's yelling at me that this type doesn't match that type. Oh, I know, I'll just call this typecast function to fix it. That's not going to work, right? I mean, it could, if you had that, it would work. It would like stop yelling at you, but then it would probably crash. And by the way, Haskell does in fact have a function called unsafe course, which does this, but you shouldn't use it. It's very unsafe. It's like, if you're sure you know what you're doing, then you can just tell the type checker to shut up. And if it crashes at runtime because it tried to use some bits in a way that didn't make sense, like that's on you, right? So, impossible, except, well, it is possible. All right. Let's do A arrow list A. All right, chat with your neighbors. Come up with some examples of functions of this type. Well, maybe come up with some examples of functions that do have this type, and then also maybe think of some examples of things that a function of this type could not do.
Already.
Yeah, but that's going to be pretty confusing.
Oh, I just said
They're just kind of
create a
all
list.
the same.
Just feel like
You
there's
could do that. Or you could create a list of all the,
Of type A. All the elements are A.
it's empty. Or it's empty.
Yeah.
Or one or more of them. So yeah.
All right, let's have an example. Could a function of this type do? Lee?
You could take in like X,
Yeah.
call it, and then make a list that contains just
X, so like cons X empty.
yeah.
Yep, that works. That works. What else? Anything else that would work? Henry?
You can just return an empty list.
Okay, yeah, I could. So, I could say, I don't care about your X, I'm just going to give you empty. That works. Anything else that would work? Yeah.
And you could do it with technically any number of the same X.
Yeah, so we could also do like, P4, okay, wait, so this should be, there's a better naming scheme for these now, right? So 0, 1, 2. This one should be called P4 0 because it makes 0 copies of X. This one makes 1 copy of X. This one makes 2 copies of X. Right? And so on. But fundamentally, this is all like, really your only choice is how many times you're going to copy X. That's your only choice. Because you cannot manufacture new values of type A out of thin air. You only have the one value that you're given, and that's the only thing you can use. So fundamentally, a function of this type can only make a list with some number of copies of the input. Okay, cool. So I mean, essentially functions of that type kind of correspond to natural numbers, like for each natural number, well, each natural number plus infinity. Because you could also decide to make an infinite list. Here, let's just for fun. 4 underscore.
That's true.
Can we do this?
Yeah, but it's so
Does Haskell consider that? No, that's a parse error. All right.
numbers infinite.
T4I x equals cons x T4I x. Cool. Yep, that works too. Okay, one more. P5. List A, arrow, list A. All right, talk to your neighbor again. Could this do?
You can completely disregard the list and return an empty list. Theoretically, you could just take a singular element out of the first list and return that.
Yeah, reverse, reorder. You could randomize. You could have it completely change to random order. You could sort it. You could, in theory, do any permutation of any combination. You could do a permutation of all elements.
Yeah.
All right, so let's hear some examples.
The list 18 times.
Just yell them out. What kinds of things? Because I won't necessarily implement them all, but
You could remove an item, we did that earlier, right?
yeah, it's like it could, P5 could, remove an item. Yeah, like, remove the first item, if there is one or something. Yeah, what else?
Empty list.
Could just return the empty list, right? All right, what else?
Reverse it.
It could reverse it, yep. Other examples?
Double itself.
Yeah, it could, so like it could, double every item. Not in the sense of like multiplying by 2, but in the sense of like copying it. So if you had like 1, 2, 3, now it would be like 1, 1, 2, 2, 3, 3. What was that? Yeah. What else?
You could, in theory, make any kind of permutation of all the elements in both lists.
Yeah. Any permutation.
It could return itself.
It could be the identity function. I don't know why I'm putting these all above reverse, but I don't know. Reverse just feels like it needs to go at the end. So. Yep. Yeah, it could like, drop some and duplicate, triplicate others and like mix others. Right, so you can kind of do any combination of removing elements, like duplicating them or mixing them up. What it can't do is make up new elements that weren't already in the original list, right? So like if you called this function with a list containing the numbers 1, 2, 3, without even looking at how this function is implemented, you're going to get a list out that only contains the numbers 1, 2, and 3 in it. It could be in a different order, it could be like duplicated, it might not have all of them, but it's not going to have 4, right? Because this function can't possibly make up things of type A if it doesn't know what A is.
What if the function was literally add 4 to a list? And it was like you literally you set the whatever value in.
Yeah, so you mean like, what if we try to make a function that said like, just like add 4 to the beginning?
Yeah.
Yeah, that's a type error. Because it says, hey, you use the number 4, and basically it's saying like, I don't know that we can do numberish things with the type A. That's essentially what this type error is saying. But yeah, because we promised to work with any type of list you want, but we are now returning a list that has an int in it, and that might not be the type that was chosen. Right. So it doesn't work. Good question. Actually, I also heard someone say we could sort the list. We actually can't. Right? Why can we not sort it? Yeah.
How would you sort things like bools or strings, I guess?
Well, I mean, you could just decide that false is less than true, You could just, strings are in fact, you can sort strings like alphabetically or something, right? Yeah, there's a more fundamental reason, yeah.
So we can't compare them because, I mean, like, it's kind of like list A is a black box. We don't
Right.
know what's inside it. We don't know how to compare it.
Exactly, right, because we don't know, we don't know anything about the type A, so we don't know how to compare things in type A. It might be possible to compare them. Now, if we were given, like, so maybe I'll do this in a different example, right? So P6, I'll just say P5 or something, right? If we were given a function that says, hey, I will give you I will choose a type, so the caller of the function says, I will choose a type A, any type I want, but then I promise I will give you a function that takes 2 of my A's and returns bool. And we think of it like a comparison that says, like, is this less than that? And then I'll give you a list of A's, right? This could sort, because when it wants to compare things, it could just call this function that was provided. It's like your friend hands you a big list of boxes, and like, you can't open them, but if you hand me 2 of them, I'll tell you which is bigger, right? And then give them back to you or something. That would work, but this could sort. I will leave that as an exercise, implementing a sorting function. Right, but fundamentally, the elements of the output all had to come from the input. It can only drop, duplicate, or reorder. Okay. But I want to make the point here. So, I mean, when we started out, just like the fact that arrow A can only be the identity function is not that useful of a fact. I mean, like, it's not that often that you would just see something of type A arrow A, right? But now we're getting into territory like this is actually more useful. And it goes both ways, right? If you see a function with a polymorphic type, that tells you a lot about what that function can and can't do, right? Which can be helpful. But also, if you're implementing a function of this type, right? So let's suppose that you had a list of integers, and you wanted to do a certain like rearranging operation on them. You're like, maybe I want to swap the first 2, and then swap the 3rd and 4th, and then swap the 5th and 6th, right? Something like that, right? So you know that you have a list of ints, and you're going to only do this on your list of ints. So you could just sit down and write a function of type list int to list int that went through and like swapped them. But if you're like, wait a minute, this function doesn't actually depend on the fact that they're ints, right? So if you give it this more generic type, that's actually really helpful, because now the compiler, the type checker, is making sure that you don't accidentally do something that would only work on ints, right? That you're only allowed to like reorder them. And so it actually helps you writing the function, because it constrains what it can, there's fewer mistakes you can make, right? Because you basically restricted yourself from being able to do things that you don't want to do. This is a great example, right? Yeah, you could write if you know you want to sort a list of ints, you could write a function that just says give me a list of ints and I'll give you a list of int, right? But if you write it in this generic way, like, it has a lot better chance of being a correct sorting algorithm if you know that it does not actually, it can't care about what the specific values are. The only thing it can do with them is compare them to see which is bigger, right? Now, it doesn't guarantee it's a correct sorting algorithm, right? You could just ignore this function and return the same list, or you could have just like gotten something back. But there's still, of course, mistakes you can make, but it cuts down on the number of mistakes you can make, or I'll say there's certain mistakes you can make that would actually turn into a type error instead of just being like giving you the wrong answer. So yeah, in general, as you're writing things, right, number one, of course, you should think about pulling out pieces of what you're doing into individual functions. And often, individual pieces of what you're doing, actually, you can make them polymorphic in some way, and that can be really helpful. Even if you know that you're only going to use them at one specific type, it can still be helpful to give them the most generic type that you possibly can. And sometimes you can figure out what that is, and you just write it down. Sometimes you can write a function. For example, let's say you want to do that, swapping ints thing, but you're not sure what the most generic type would be. You could write the function with a specific type, and then comment out the type signature, and then basically ask GHC to infer the type for you, and it will infer the most general type that it can. So if, in fact, it could be polymorphic, it will tell you that. I don't know if I can show you an example of that. Well, if we did like well, we'll just do our like removing right. So I gave it this specific type, but if I comment this out and I have it, see, it inferred that it actually has type list A arrow list A. I could be like, oh, cool, I'll use that one general type. Okay. Questions do you have? All right. Trying to think what time I have here. Yeah, okay. I think it's not quite up. So, I will say one thing I do want to talk about at some point, and so maybe we'll talk about this briefly next Tuesday. But so I just showed you this process, that Haskell can. I mentioned this before, but I just showed you how if we don't put a type for something, Haskell GHC can just infer the type, can figure out the type. And actually, even when you do put types for things, it's still doing some type inference in the background. So for example, right, the fact that any polymorphic function takes a type as an extra argument, but normally Haskell just figures out what type has to go in there, it's this exact same process. It would be extremely tedious if you had to put every single type argument every time you call a polymorphic function, right? So it can be nice to like understand in a little bit more detail how the language does that. Like how does it look at some code and kind of figure out what type that it has. Maybe I'll just say really briefly in this example kind of generally what it's doing, and then maybe on Tuesday we'll talk a little bit more formally about how it works. But in this case, it's like, okay, what type does P7 have? Well, first of all, it can tell that it's a function because you are applying it to you're defining it applied to some arguments, right? So it's like, okay, P7 is a function from something to something. And then it's like, okay, what are you applying it to? Oh, empty and cons. Oh, those are constructors. Those have type list something, right? So actually, I guess the input type to this function must be a list of some type. It's not sure what type yet. And then it can also look at the output type and be like, oh, well, you're also outputting something of possibly a different list type. At this point, if it just looking at this line, it can figure out that it's something like list A to list B. It's this line where it says, oh, you took as input a list A, so this L is a list A, and then you output the same thing, so actually it must be list A to list A. So it's basically like looking at different places that functions are applied and kind of learning something from each one, like when different types have to be the same. And then it's just doing a whole bunch of rewriting and substitution, basically to like solve a big list of equations. It's like, oh, this type is equal to this type, and this type is a function, and this type, right? And then it just like solved it. And if there's any variables left, It's like, oh cool, I never, like, I had this type A and I didn't know what it was, but I never found it, that it had to be equal to anything else, so I'll just make that, it's just polymorphic, because that means it can work for anything. Anyway, we'll probably talk about that in more detail on Tuesday. All right, we'll do our quiz, and